In this video, we are going to talk about electrolysis. We will also go through some practice questions with regard to electrolysis. We will also be learning how to predict reactions using the electrochemical series, as well as some exceptions to the rule. So in the previous video, we have talked about a galvanic cell. So what is the difference between a galvanic cell and also the electrolytic cell? Galvanic cell and electrolytic cell. So in a galvanic cell, what we are actually doing is we are exploiting spontaneous redox reaction. So remember the rule we have learned before. If we have two species and then they have a negatively sloped line, they will react spontaneously, with the top left species being reduced and the bottom right species being oxidized. So it will happen naturally. When you put them together in the same container, they will occur without generating electric current. But if you separate them into two containers, which we call them galvanic cell, then we can generate electric current. In particular, another interesting fact about spontaneous redox reaction is that it is exothermic or produces energy. A very good example is the combustion reaction, which is spontaneous redox reaction, and it produces energy and produces heat. And we know that anode corresponds to oxidation and cathode corresponds to reduction. We also went through the reasoning behind this, because the negative ions goes towards anode, the positive cations goes to cathode. So that's the reason it's called anode and cathode. And the polarity of electrode depends on the reaction itself. So suppose this beaker, you put in a very strong reducing agent, so it will be oxidized. Since it will be oxidized, electrons are leaving this electrode, so it is negatively charged. Conversely, on this side, if you have a very strong oxidizing agent, so it wants to be reduced, electrons will flow towards this terminal, and opposite attracts, so it's positively charged. And if I reverse the order, then the polarity will also switch. So that's basically a summary of galvanic cell and spontaneously redox reaction. Electrolytic cell is very different. So it conducts something called electrolysis. And electrolysis is non-spontaneous. So it's actually just the reverse of spontaneous redox reaction. So what happens is actually you have this setup going on. So they are positively sloped. So as we discussed in the last video, when this is the case, we don't get spontaneous redox reaction. The species prefer to stay where they are. But for electrolysis, we are using energy to force this non-spontaneous redox reaction to occur. So we are forcing it. And this species will be reduced to the bottom left. The top right species will be oxidized. And just an aside, these two products, when they come into contact with each other, they would react spontaneously. So perhaps it's a good idea in an electrolytic cell to not let these two things contact each other. Otherwise, we will just go back to the original form, because we are forcing the reaction. So because it requires energy, it's endothermic. You can also think this from another perspective. Since the spontaneous redox reaction is exothermic, then the reverse must be endothermic. And perhaps the most confusing aspect of electrolytic cell is the polarity of anode and cathode. So here, anode is positive, cathode is negative. But the definition of anode and cathode still applies. So anode is still site of oxidation. Cathode is still site of reduction. A very good way to think about this is that for the anode part, you are extracting the electrons using the power source. So it's because electron is negatively charged, so anode will become more and more positive. So that's why the polarity is positive here. And for cathode, because you are dumping electrons in cathode, so it is negatively charged since you get a lot of electrons. Whereas for the galvanic cell part, you are actually, the electron are actually leaving anode spontaneously. And because we know that when something are the same charge, they will repel each other. So that's why anode is negative in the galvanic cell example. And we also know that an opposite attracts. So because the electron is negative and the electron is flowing towards cathode, cathode is positively charged. So in the end, it's just because for the galvanic cell example, it is happening spontaneously, happening automatically. So we can use the positive same charge repel, opposite attracts argument. But for the electrolytic cell, because everything is being forced, then we use the argument about withdrawing electrons to make anode more positive, and dumping electrons to make cathode more negative. So two different arguments based on two different scenarios. And the polarity of electrode really depended on how the external power source is connected. So that's just a very broad overview. Let's now go into more detail. The electrolysis is a chemical reaction caused by passage of electric current through an electrolyte. Electrolyte can be molten, in which case it is actually a liquid, or it can be aqueous solution. We will discuss the significance of electrolyte later. And the reaction we have already discussed is endothermic and absorb energy. The place where electrolysis occurs is called electrolytic cell. So what does an electrolytic cell looks like? So instead of 2 containers, we only have 1 container. Because we are forcing a non-spontaneous reaction. So we don't need to worry about the reactants reacts with each other, since they would not react naturally. The only thing we need to be careful with is we do not want the products to get into contact with each other. So we still have 2 electrodes. And we also have something like this. So this is the power source. And the long bar is the positive terminal of the power source. The short bar is the negative terminal. So you need to remember this, otherwise you will be confused. We still have the electrodes. And let's look at the polarity of the electrodes. So we know that the long bar represents positive side, the short bar represents the negative side. So from the introduction here, we know that anode is positive. So essentially what this positive terminal is doing, or what this setup is doing, is that the positive side of the power source attracts electrons. And the negative part of this power source repels electrons. And following on the argument we already discussed before, because we are withdrawing electrons, so this electrode becomes more and more positive. So it is in fact positively charged. And because we are dumping the electrons at the left electrode, then it's becoming more and more negative. So it is negatively charged. And since we are extracting electrons here, this is the anode. So no matter whether you are dealing with galvanic cell or electrolytic cell, the definition of anode and cathode is unchanged. Anode corresponds to oxidation. Cathode corresponds to reduction. And since we are losing electrons, this means we are undergoing oxidation on the right. And on the left, since we are gaining electrons, this means we are undergoing reduction. So it is the cathode. Maybe I write it down one more time. And now let's look at the choice of electrolyte. It can be either molten liquid or it can be aqueous solution. So for molten liquid, usually it's very, very hot, more than 1000 degrees. And this type of electrolyte is actually very common for the production of certain metals. And we will cover this very shortly. For aqueous solution, one thing to remember is that it contains water. And this becomes very important when we are trying to predicting what will be formed in this electrolytic cell. And I want to note, the electrodes can be inert or it can be active. But no matter what electrode you use for the cathode, it would always be inert or always not react. So whether you put in a very reactive metal, or you put in inert electrode, or you put in gold, whatever, doesn't make any difference. So why is this the case? Cathode is undergoing reduction. So electrons are entering cathode. And we know that metal can only undergo oxidation. So metal can only ever lose electrons. It cannot gain electrons. And because cathode is gaining electron, so the metal will never react. But for the choice of anode electrodes, you need to be very careful. If you don't want your electrodes to react, stick with the inert electrode. If you choose any active or if you choose very reactive metals, then maybe the anode electrode will actually react. So now let's move on to the very fun part. Predicting the product of electrolytic cell. So again, this is your very good friend, electrochemical series, very important piece of information in your data book. It is even numbered as 1, so must be very important. And we need to rely on the electrochemical series to predict the products of electrolytic cell. So the first thing we want to do is we want to know, so by reading the question. So the reading of question is very important here. So you need to know what species you have. So this can include ions in electrolyte. So perhaps you have the potassium nitrate electrolyte, then the K plus ion, and the nitrate ion. They could potentially react. And you need to look at the electrochemical series to see whether they are present. Here, the nitrate ion cannot be found on the electrochemical series, so you just ignore it. What is more important, perhaps, as I have already explained before, is water in the aqueous electrolyte. And this is very problematic. If you look at H2O, it appears in many places on the electrochemical series. So if you have aqueous electrolyte, then potentially the water will actually react. You also need to look at your electrodes. But this is for anode only. So don't worry about the cathode, because cathode is receiving electrons. And when metal receives electron, it will not change to anything else. Then let's recap some of the characteristics of electrochemical series. So from the top right down, you are moving from the weakest reducing agent to the strongest reducing agent. So why is the fluoride ion the weakest reducing agent? There are 2 ways to think about this problem. The first way is because the fluorine gas is the strongest oxidation agent. So it really wants to undergo reduction and really want to become the fluoride ion. And because it really wants to become the fluoride ion is very stable. And the second way to think about this is because the fluoride ion is very stable, doesn't want to undergo any reaction anymore. So it's the weakest reducing agent. It really doesn't want to undergo oxidation. Conversely, the bottom left is the weakest oxidizing agent. So the lithium ion really doesn't want to become lithium metal. So this is very important. Remember that in the galvanic cell example, we are looking from the top left to the bottom right. So why don't we do this for the electrolytic cell or the electrolysis reaction? It's because if you go from here, so if you can actually find something on the top left and bottom right and then connect them in a line, you get a negatively sloped line. So in this case, we are actually undergoing a spontaneous redox reaction. And if that's the case, then the question is wrong. So the question is trying to ask you about electrolysis, but it gives you a spontaneous redox reaction. So it would never happen for a question related to electrolysis. What would happen is you go from the bottom left to the top right. So you actually get this positively sloped line. And when we have a positively sloped line, we know that we have a non-spontaneous redox reaction. And that's when electrolysis becomes important, because we can force this reaction to occur. So that's why we look in this way. So now let's look at how do you predict which reaction would occur. So I think this can be best done by actually using a practice question. And this practice question, I would say, is a little bit more difficult. So in the exam, you should expect to see a question with similar difficulty. So we have electrolysis of a 1 molar magnesium iodide with inert electrodes. So that's when reading the question becomes very important. The 1 molar indicates or implies that you have aqueous solution. An aqueous solution means you have water present. And we know that water is a very big problem when you are doing electrolysis. So what I recommend you doing is you highlight everything with water here in your electrochemical series. So you don't forget you actually have water there, because it may actually react. So there are 4 places where you can say H2O. I mean, for those reactions, unless you have these ions present, you don't need to worry about them. In this case, we do not have these ions present, so we can just safely ignore them. And also be careful of this is H2O2, it's not water. Okay, so let's look at what species is present. So we know that water is present. We also have the negative iodine ion present. We also have magnesium ion present. So this 3 is the only species present in our system. So let's look at their relative location. Also, maybe it's useful to note the magnesium ion can only undergo reduction. So it can only gain electrons to become magnesium metal. And we have inert electrodes, so we don't need to worry about the choice of electrode or the potential for the electrodes to react. And the I- ion, it can undergo oxidation at anode. And water, is, as you can see, is appearing on the right-hand side and left-hand side simultaneously. So it can undergo both reactions. Undergo both oxidation and reduction. So from the electrochemical series, what we are trying to do when predicting the reaction is we want to find the 2 closest species. So for example, if we have lead and hydrogen gas, we can connect them via a positively sloped line. And they are very close to each other compared to nickel ion and hydrogen gas. Because they are close to each other, you can just remember this, they are easier to react. Another way to look at this is that we know that hydrogen gas is a reducing agent. And here we are going from bottom to top. So we are actually having increased strength, increased power of oxidizing agent. So in other words, the lead ion is a more powerful oxidation agent than the nickel ion. Because the lead ion is a more powerful oxidizing agent, it really, relative to nickel ion, really want to gain this electron. And for the given strength of reducing agent, the species that really want to gain electron would be preferentially reacted. And so that's the reason why the lead ion is preferentially reacted. So when it's closer by, it's actually easier to react. When they are further away, it's more difficult to react. So we can even look this from a different angle. If we have copper ion, which is even a more stronger oxidizing agent than the lead ion, and in fact, a more stronger oxidizing agent than the conjugate of hydrogen gas, which is the H plus ion. You don't require any energy for them to react. They will react automatically. So in this way, the spontaneous and non-spontaneous reaction, they are actually connected. We get spontaneous because because the copper ion is very powerful, even more powerful than the redox conjugate of hydrogen gas. So they will actually preferentially react. And in the case of nickel or lead, because the conjugate of hydrogen gas is a stronger oxidizing agent than the lead ion, you need energy. You need to actually put in rather than produce or make energy for this reaction to occur. So this is how you predict whether the two species would react. You can try to understand this by using the argument with oxidizing agent and reducing agent. Or you can just remember, if something are closer to each other, they will preferentially react. So what is the voltage required for the two species to react? So in this example, the voltage is just the difference in the potential voltage. So you require 0.13 volt for lead ion and hydrogen gas to react. In the case of nickel ion and hydrogen gas, you need to require 0.25 volts because it is more difficult to conduct this kind of reaction. Also, a problem to note is about a thing called overpotential. So if you have both lead ion and nickel ion present in your system, and you apply a voltage of 0.25 volts, then it's very likely that both the lead ion and the nickel ion will react. Because with 0.25 volt, or even something greater than 0.25 volt, it is possible that both two reactions would occur. So if you only want to produce perhaps lead metal, you should only apply a voltage of 0.13 volt. If you overpotential, in other words, you apply too much voltage, then other reaction may happen. And this is unwanted if you only are looking for the lead metal rather than the nickel metal. So they really like to ask this kind of question in the exam. So be very careful about this. So now let's go back to our question. So we know we have water present. So maybe it's helpful to find where water is in our electrochemical series. Starting from the right hand side, so it's addressing the possibility for water to undergo oxidation. We have water here. We don't really need to worry about this, as we have already discussed, since we don't have those ions present in our system. We have water here. Yeah, and I think that's it. So, and then let's look at the left hand side. We have water here. We also have water here. And now let's look at the I minus ion. And it is here. And can only undergo oxidation at the anode. The magnesium 2 plus ion is here. So that's all the species present in the system. And based on the rule we have discussed before, we want to find the two closest species, and they will be the one reacting. So perhaps let's rule out some possibility first. This reaction is not possible because we do not have a constant supply of oxygen gas in our system. So oxygen is not one of the reactants. So this reaction would not be possible. And the rest of the reactions are all possible. And then we find the two closest species. So it is H2O and I minus. So why is this the case? I want to emphasize this again. So for the three species present in our system, the I minus ion is the strongest reducing agent. And the water is the strongest oxidizing agent. In all redox reaction, the strongest reducing agent will react with the strongest oxidizing agent. So that's why the two closest one would react. You can also get magnesium and this water react, but you need to put in a lot of energy, as we discussed before. So 1.77 plus 2.37. You need to put in more than 4 volts of energy for them to react. So very, very difficult thing to do, although not impossible. So with this information, we can write down the oxidation reaction. So it is always the easiest reaction for us to do. And this is the oxidation. Reduction is the reduction of water. And the overall reaction, we just combine them together. And the electrons cancel out as expected. We do not want to see any electrons in our final equation, since no electron can be created or destroyed. So what is the potential difference required for this reaction to occur? It is 0.54 minus, which is 1.37 volts. If you put more than 1.37 volts, really okay, as long as you don't go too much over this. If you go like 3-4 volts, you can get secondary reaction. So the other species in your system may actually react if you overpotential your cell. Okay, so this is an example question. So let's now look at another example question. Question 2. We have molten electrolyte. So you should be very happy when you see this term, because you don't need to worry about water anymore. And we also have inert electrodes. So this is also good news. You don't need to think about what's going on in the electrode. And we have zinc chloride. As the molten electrolyte. So this may be the carbon electrode. So let's have a look which reaction would occur. So we have the zinc 2 plus ion. So it can only ever undergo reduction. So reduction happens at the cathode. So I have the chloride ion can undergo oxidation at the anode. And I mean, it's always possible as long as you put in enough voltage. So let's have a look. The zinc ion is here. Chloride ion is here. So chloride ion be oxidized, zinc ion be reduced. 1.36 volt, negative 0.76 volt. So we have all the information we need. So the reduction equation, you can just copy directly from the electrochemical series. Remember the state is liquid, not aqueous, because we have molten electrolyte. Can be solid or liquid, depends on the temperature. And the chloride ion, we have 2 chloride ion, goes to chlorine gas plus 2 electrons. And the voltage required is 1.36 minus 0.76. Is 2.12 volts. Third question. We have molten electrolyte and reactive electrodes. So for the cathode reaction, for the anode, we need to have a sink. We don't need to worry about what will happen for the cathode electrode, because cathode undergoes reduction and metal cannot gain electron further, it can only lose electron. That's why no matter what the electrode at cathode is, it's always inert. So let's perhaps list the species present in our system. So we have a molten electrolyte, so we don't have water present, which makes us job much easier. So we have lead ion, we also have chloride ion, we also have copper. So the lead ion, because it's already in the ion form, can really only undergo reduction. The chloride ion can undergo oxidation and cannot undergo reduction. And the copper metal can undergo oxidation at the anode. So that's everything we have present. Now let's go back to the electrochemical series to see or to predict which reaction would occur. So maybe let's clear this up a little bit. We have lead ion we also have chloride ion, and we also have copper. So which two species are the closest? Is the lead ion and copper. So these two will preferentially react with a given voltage. We can also calculate the voltage required, which is 0.34 minus negative 0.13. So the voltage required here is 0.47. And the oxidation reaction, as we have seen from the electrochemical series, is the oxidation of copper. Reduction reaction is the reduction of lead ion. Note, lead can be in both liquid or solid form. Really depends on the temperature of your container. So this is the answer for question 3. The voltage should be greater than 0.47 volt. I should say greater or equal to. Now for question 4. We have aqueous electrolyte, inert electrodes. So the electrolyte is 1 molar Hi, and electrode is carbon. So because we have aqueous electrolyte, we now have water present. And usually, whenever you see this case, you need to be very careful, because there are so many possible reactions that water can undergo. We also have H plus ion, I minus ion. Yeah, that should be everything we have. Water can undergo both reduction and oxidation. The H plus ion can really only undergo reduction. So it can only undergo this direction when viewing from the electrochemical series. The H minus ion, because it's already have lots of electrons, can only undergo oxidation, so it goes in this direction, and water can go in both directions. And now let's go back to our old friend, the electrochemical series, and then list everything present. So as before, we have water. We also have I minus ion, which is here. We also have H plus ion, which is here. So the two closest are actually I minus ion and H plus ion. So in this case, although we have aqueous solutions, it really doesn't matter. The voltage required is 0.54 minus 0. So as long as we are bigger or equal to 0.54 volt, we can force the reaction between I minus ion and H plus ion to occur, in which case the I minus ion would undergo oxidation and H plus ion would undergo reduction. And this shouldn't be a problem, since the resultant product is a solid and gas. So the H2 gas, hydrogen gas, would escape the system. So the two products would not come into contact with each other. And this is very desirable, because if they come into contact, then the spontaneous redox reaction would occur, and everything we did would be essentially reversed. So let's write this down. The oxidation, and you just copy this down directly from the electrochemical series. Once you have done enough practice, you should be able to write this out without even looking at the electrochemical series. And the required voltage, as we have said before, should be greater or equal to 0.54 volt. And sometimes, I think in certain textbook, you get something like greater than 0.54 volt. And I actually think this should be a better answer. Because when you write greater or equal to 0.54 volt, if the voltage is exactly equal to that, you are essentially on the fence. But if it's greater than 0.54 volt, you are unambiguously greater than this required voltage. So maybe to just be safe in your exam, I recommend writing greater than 0.54 volt as your answer. So let's have a look at another question. We have aqueous electrolyte again, which is 1 molar sodium chloride, and we have copper electrode. So let's list the species present in the system. The sodium ion can undergo reduction only. The chloride ion can undergo oxidation only. But copper ion can undergo oxidation only. Because remember, at cathode, since we are receiving electrons, no matter what the electrode is, it's always inert, since metal cannot undergo reduction. But it is possible for metal to undergo oxidation. And for H2O, as we have mentioned many times before, it can go in either direction. So now let's go to the electrochemical series to figure out which reactant would occur. So again, we highlight water in the system. We have sodium ion, which is near the bottom. We have the chloride ion. We also have copper. So let's look at which two species are the closest. It's H2O and copper. So H2O would undergo reduction, copper would undergo oxidation. The required voltage is 0.34 minus negative 0.83. So actually, both the sodium ion and the chloride ion are not involved in this chemical reaction. So the oxidation half equation we'll copy this down directly from the electrochemical series. The reduction half equation so this is the reaction, And the required voltage, if you calculate it, should be greater than 1.17 volt. And it should be higher than the 1.17 because we are trying to force the reaction to occur. And perhaps we write down the overall equation as well. So we simply add the two equations together. There should be no electron present because we are not creating or destroying electrons. And there are some things you can observe during your experiment to tell that the reaction has actually occurred. So let's have a look at some cues. So you are producing the copper 2 plus ion, and this ion, when dissolved in water, looks blue. So if your solution turns blue, or if the surrounding of your anode have a bluish color, then you know that it is copper that is being oxidized into copper 2 plus ion. You can also look at cues from your cathode, which is the site of reduction. You should be able to see some gas bubbling around your cathode. And this is the sign that hydrogen gas has been produced. And a very interesting thing is this OH minus ion. If you recall from your year 11 chemistry knowledge about pH value, you know that increase in the OH minus ion would indicate increase in pH around cathode. So the whole solution around cathode should become more basic. So that's some of the cues you can tell of whether you are actually doing the desired reaction or not. And if you get any other observations or any other things that are unexpected, maybe there are some side reaction that is occurring. Perhaps you are overpotential the cell. If the voltage is 100 volts, maybe sodium ion can actually undergo reduction to become sodium metal. And the chloride ion would actually undergo oxidation to become chlorine gas. So that's some of the important signs you need to understand when conducting experiment. So I think that's enough practice for you. And I just want to make some final points. So first is metal at cathode can't undergo reduction because metal can never gain electrons. So we can choose any metal for cathode as long as so you need to notice there is no spontaneous reaction. So if you put sodium metal, this is not good because sodium will react with almost anything. The second point, metals whose ions are weaker oxidizing agent than water. So what do I mean by this? those species, lithium ion, potassium ion, sodium ion, aluminum ion, all those things below water, can never be produced by electrolysis of aqueous electrolyte. Water will always reduce in preference. These metals can only be produced by electrolysis of molten electrolyte. So I'm talking about metals: magnesium, sodium, potassium, aluminum, lithium, anything below water. The third point, which is usually assessed in the exam, is that non-standard concentrations can affect the order of half equations. In the exam, they usually like to use these three half equations. Let me highlight those three equations for you. So those three chemical equations or reactions. So as you can see, they are very close to each other. And if we have non-standard concentrations, for example, if the concentration of the bromide ion is very much below 1 mole, so maybe 0.001 mole, then what would happen is this reaction becomes very hard to do. So although we expect the bromide ion to react first, but because of such low concentration, we may actually see water reacting first. Or if the concentration of chloride ion is much greater than 1 molar, maybe like 100 molar, then the chloride ion may preferentially react. So what I'm trying to say is, if something, when they are very close to each other, have very high concentration, it would make the reaction easier to do and effectively lower the value of E naught. So it can actually move down the rank. Conversely, if something has very low concentration, it can actually move up the rank, so it becomes harder and harder to do. When the concentration becomes negligible, then it is almost impossible to reduce or oxidize this particular species. And in the exam, they will ask you questions like, oh, we have both bromide ion and chloride ion in our system, but why does we see a production of chlorine gas? And you would say, if that's the case, the concentration of chloride ion is much greater than 1 molar, much greater than the standard condition. So that's why we actually see the production of chlorine gas at the anode instead of the production of bromine liquid. And they also sometimes ask you very indirectly. So you know the color of bromine liquid is brown, dark brown color. So in the exam they will say, oh, we don't see any change in color around the anode, but we see some bubbling of gas. Then this tells you two things. So either we see the reaction of chloride, or it's actually water that is reacting. So we see the production of either oxygen gas or chlorine gas. But in any case, the correct answer is because the concentration of bromide ion is too low, either water or chloride ion are preferentially reacted. So that's how you answer those kind of questions. So this third point is really, really important.